Welcome to the SPI Interface course of the HT8 MCU Basic Tutorial. This course will take you through the SPI Communication Interface of the HT8 MCU from the following 7 sessions. Communication Interface Introduction, SPI Interface Introduction, Relevant Registers, SPI Communication Process, SPI Configuration, SIM Independent Interrupt, and Application Examples. Communication Interface Introduction. In practical applications, a single chip may not be enough to implement all functions that the product wants to achieve. For example, in a certain product, the main control MCU is used to implement key functions and temperature measurement. Its remaining resources, or I/O ports, are not enough to implement the display function. In this case, we can use a display driver IC to realize the display function. However, how can the functional data implemented by the main control MCU be displayed on the screen? This requires a communication between the main control MCU and the display driver IC. The main control MCU sends the display data to the display driver IC, which then controls the display on the screen. What are common communicate interfaces in the HT8 MCU? In the HT8 MCU, there are SPI Interface, I2C Interface, and UART Interface. The SPI Interface and I2C Interface are included in the same serial interface module, which is called SIM, and only one interface can be used at a time. The full name of SPI is Serial Peripheral Interface, the full name of I2C is Inter-Integrated Circuit, and the full name of UART is Universal Asynchronous Receiver Transmitter. The SPI uses 4 signal lines, which are the synchronous clock line SCK, the data input line SDI, the data output line SDO, and the slave select line SCS. The I2C uses 2 lines, which are the data line SDA and the serial clock line SCL. The UART uses 2 lines, which are the data receiving line RX and the data transmitting line TX. The SPI communication is carried out in a master-slave mode, where the master controls the synchronous clock signal. The SPI communication allows a single master to communicate with different slave devices by controlling their chip select signal line. Similarly, the I2C communication is also carried out in a master-slave mode, where the clock line is controlled by the master, data transfer is controlled by the clock signals, and the master distinguishes between different slave devices by their address. However, the UART interface does not have a master-slave relationship. The SPI is full duplex synchronous, the I2C is half duplex synchronous, and the UART is full duplex asynchronous. The full duplex communication allows synchronous data transfer between both sides, while the half duplex communication only allows one data transfer direction at the same time. For the synchronous communication, the master generates synchronous clock for the transmitter and receiver, while the asynchronous communication has no synchronous clock line. Regarding the communication speed, the SPI is faster, the I2C is medium, and the UART is the slowest. The SPI interface is usually used to communicate with external devices that require high-speed drives, such as flash and screens. The I2C interface is usually used to connect multiple sensors for data sampling and transmission, such as temperature and humidity sensors, and double EEPROM memory. The UART interface is generally used in one-to-one communication, such as to drive a Bluetooth module or a Wi-Fi module, or to work with an external serial port module to print the debugging information. SPI Interface Introduction. The SPI interface is a synchronous, full duplex, serial data transmitter and operates as a master-slave type, which is usually used to communicate with external devices that require high-speed drives, such as flash and screens. For more details, Please refer to the application note, HT8 MCU SPI Application Guidelines and Example, on Holtec's official website. Synchronous means the clock signals of the transmitter and the receiver must be the same, with the master providing the clock to the slave. Full duplex means to allow synchronous bidirectional data transfer between two devices. And serial means to use one data line to transmit data bit by bit in sequence. Then what is a master and a slave device? The SPI interface of the HT8 MCU supports the master mode and slave mode, which is selectable. The master device actively receives and transmits data, while the slave device passively receives and transmits data. The SPI interface has 4 lines. SCK is the serial clock line, which is used by the master to provide clock to the slave. SDI and SDO are data input and output lines, which are used for data transfer. SCS is the slave select line, or known as chip select line for slave device selection. When the master wants to communicate with a certain slave device, it first needs to pull low the chip select pin of the slave device. For example, there is 1 master and 3 slave devices, then how to communicate? The master's SCK, SDO, and SDI pins are directly connected to the corresponding pins of the 3 slave devices. Then 3 GPIO pins are required to connect to the SCS pin of the slave devices. The slave chip select pin is low active, so when the master GPIO1 outputs low, GPIO2 and 3 output high, the master communicates with slave 1. When GPIO2 outputs low, the master communicates with slave 2. And so on. Introduction to relevant registers. As the serial interface module of the HT66F3195 has integrated the SPI and I2C interfaces, and the SIM relevant registers contain the functional settings for both interfaces. The first register is SIMD, which is used to store the transmitted or received data. The second one is the SIMC0 register. The SIM2, SIM1 and SIM0 bits are used to configure the SIM operating mode, including the SPI master mode and master clock frequency, SPI slave mode, and I2C slave mode. The SIMDEB1 and SIMDEB0 bits take effect only when the SIM is configured to the I2C slave mode, which will be introduced in the I2C course. The SIMEN bit is the SIM enable or disable control bit. The SIMICF bit takes effect in the SPI slave mode and is used to detect whether the data transmission is normally completed. The final one is the SIMC2 register. Bit 7 and bit 6 are undefined bits. Bit 5 and bit 4 together control the SPI transmission mode. There are 4 modes. When the CKPOLB and CKEG bits both are set to 0, the SCK is high when the clock is inactive, and data is captured at SCK rising edge. When the CKPOLB and CKEG bits are set to 0 and 1 respectively, the SCK is high when the clock is inactive, and data is captured at SCK falling edge. And so on. The bit 3, MLS, is used to control the data shift order, that is the lowest bit first or the highest bit first. The bit 2, CSEN, is used to enable the SPI SCS pin function. The bit 1, WCOL, is used to monitor the data write collision. When data is written during a data transmission, this bit will be set to 1. The bit 0, TRF, is the SPI transmission flag. When the data transmission is completed, this bit will be set to 1. SPI Communication Process. The SPI communication process is divided into 3 parts: write operation, data transmission, and read operation. Regardless of the master or slave device, it has an internal TX-RX buffer. The data output line SDO and data input line SDI of the master and slave are directly connected to the buffer. The master provides clock to the slave. When the CSEN bit of the slave is set to 1, the master needs to provide a low level to the slave's SCS pin to select the slave. If the CKPOLB and CKEG bits of the master and slave are set to 0 and 1 respectively, the SCK is high when the clock is inactive without data transmission, and the data transmission starts when a falling edge occurs. Here we set the MLS bit of the master and slave to 0, so the data is transmitted with the lowest bit first. Let's start with how to write data. Actually, we cannot directly write data to or read data from the TX-RX buffer. There exists an internal data register SIMD. Write the data to be transmitted to the SIMD register. The data will be simultaneously shifted to the TX-RX buffer, then transmitted according to the selected transmission mode. Next, let's take a look at how to transmit data. When the data has been shifted into the TX-RX buffer and the first clock falling edge arrives, the lowest bit will be captured and sent out. When the second clock falling edge arrives, the second data bit will be sent out, and so on, until all the 8 data bits are completely transmitted. Then the SCK line returns to high, waiting for next data transmission. If the SIMD register is written with data during this data transmission process, a data collision occurs, with the WCOL flag set to 1. And then let's move on to the data read operation. The data received in the TX-RX buffer will be automatically shifted to the SIMD register, with the TRF bit set to 1 and the interrupt flag SIMF set to 1. Then we can read data from the SIMD register. SPI Configuration. Before using the SPI interface, the first step is to configure the SPI pins. Use the relevant pin-shared function registers to set PA1 to SDO, PA3 to SDI, PB6 to SCK, and PB5 to SCS. Then go on to configure the SPI interface. Pin configuration will be introduced in a subsequent course. The next step is to configure the SPI registers, including 3 parts. Configure SPI functions, write operation, and read operation. First, select Master or Slave mode. Here we select the SPI Master mode and set the clock frequency to the system clock divided by 4. Second, enable the SCS pin. Next, configure the transmission mode, where the SCK is high when the clock is inactive, and data is captured at SCK falling edge. Then select the lowest bit first for data transmission. Finally, enable the SPI. Now write data to the SIMD register and transmit data. Then check the WCOL bit. If a write collision occurs, it is required to clear the WCOL bit and rewrite data to the SIMD register to retransmit data. If no write collision occurs, check the TRF bit state to wait for data transmission completion. When the TRF bit is set to 1, it means data transmission is completed, and data can be read from the SIMD register. Then clear the TRF flag to 0. SIM-independent interrupt. As the serial interface module of the HT66F3195 has integrated the SPI and I2C interfaces, this means that serial interface module interrupt, or known as SIM-independent interrupt, is triggered by the SPI or I2C interface. Each time the SPI interface transmission is completed, the TRF flag will be set to 1 to trigger an interrupt request, then the SIMF interrupt request flag will also be set to 1. So what is the role of the SIM-independent interrupt? During data transmission, the CPU does not have to wait and can handle other tasks to speed up the operation. Here is a SIM-independent interrupt example. First, define the interrupt name. Then look up its interrupt address. An independent interrupt corresponds to a unique interrupt event. After the program enters the interrupt, the subroutine can handle the interrupt event. Application examples. How does an SPI master transmit data? This example sets the HT66F3195 to the SPI master mode and uses time-based to regularly transmit data. Let's check out the main program. Firstly, define a bit to store the data transmission state. 0 means not to transmit data, 1 means to transmit data. Define a variable to store the data to be transmitted. And configure the time-based 0 relevant parameters. Secondly, configure the SPI pins. Next, configure the SPI to master mode. And enable relevant interrupts. Then determine whether to transmit data. If yes, the main program will jump to the SPI data transmission subroutine. Now go on to write the time-based 0 interrupt subroutine program. The interrupt is triggered regularly with the flag set to 1. This makes the master transmit data at a fixed time interval. Finally, write the SPI transmission subroutine. Write the data to be transmitted to SIMD. Check the WCOL bit to determine whether a write collision occurs. If no, continuously check the TRF flag state to wait for the data transmission completion. How does an SPI slave receive data? This example sets the HT66F3195 to the SPI slave mode. Let's check out the main program. First, define a bit to store the data reception state. 0 means data is not received or received unsuccessfully, 1 means data reception is normally completed. Define a variable to receive data. And configure the SPI pins. Next, configure the SPI to slave mode. And enable relevant interrupts. Then check whether the data reception is completed. If yes, user can use the received data as needed. Finally, write the SPI interrupt subroutine. When data transmission is completed, an interrupt will be triggered. Check whether the data transmission is normally completed. If yes, read the received data. Course summary. In this course, we have learned the HT8 MCU's SPI interface, SPI Communication Process, SPI Configuration, and SIM-independent interrupt. Hope you will have a better understanding of the SPI interface through the learning of this course. Holtec has a professional service team to assist in development design and after-sales service. Please feel free to contact our business departments for more detailed product information and consultation services.